All right, so tonight, now we're going to talk about section 1.3, talking about lines and planes, the equations thereof. Okay. Now, obviously, a line is in line. We think about it as in two dimensions. Okay, it has here's a point, and we have some slope, right? Okay, piece of cake. And we've seen them over the years, y equals mx plus b, of course. And we've seen ax plus by equals c. We've seen them in a variety of different ways. And of course, we'll continue to do that. Okay. Then, what is a plane, or what is the difference between a plane and a line? Okay, well, now, a plane, obviously, I think it's pretty obvious. Instead of going through 2 points, it has to pass through 3 points, right? And so maybe you remember this back in the day, geometry class, you would draw it up and it would go through 3 points. Obviously, it goes on forever, but those 3 points lie in the plane. And so we're going to talk about kind of this overall. Tonight will be the first time you see it. Later on in the term, after we learn cross product, we'll get more into in a little bit more of a deeper level. Something I'd like you to think about is this. You need 3 points because to make a plane, there must be 2 vectors. And to get 2 vectors, there's got to be 3 points at least. That is, I start here, go to here, for instance. Start here and go to here, for instance. Okay? Obviously, I could have used this vector in this case. There's actually 6 vectors here. If this is A, there's also negative A. Okay? There's obviously B, and then, of course, negative B going the other direction. And then, of course, you got C and negative C as well, right? So with 3 points, you technically have 6 vectors to choose from. You must have 2 vectors to pull off a plane. Okay? So 2 points, I can create a line. 3 points, I can create a plane. Now, what must be true about those points is this. They cannot be on the same line. Are you with me? Because I say I created this vector. Well, guess what? This is the same vector, dog. That's not helpful. Okay? So they cannot be collinear. I need 3 non-collinear points to create a plane. That's something that you learn in geometry at some point back in the day, undoubtedly. Or maybe you slept through geometry like I did. But in theory, you're supposed to learn that. And so now this stuff is we're recalling it back to memory a little bit, / teaching it to you for the first time. One moment, please. Oh, shoot. Now, when we think about that, that's a big deal. So we're not going to get too much into the why tonight, but I find that to me, it's just easier to tell you that right now. Okay? Now, if this is a plane, what you'll notice is obviously this goes off, out into all directions. Yes, it goes out this direction, but only in the plane. So what I like to think about is this. Here's the front of the classroom, perhaps. Here's the chalkboard. That's a nice chalkboard, Jay. The chalkboard is a plane, okay? Everything on that chalkboard, and it continues off into outer space all along that front wall, is in that plane. But if you are sitting back here somewhere, nice hair, man. That's hot. Love it. I don't know what you're doing. I guess you're standing up. Good for you. You are not in the plane, okay? And so as a result, only the points that are on that plane, obviously, only the points that are on that plane actually show up in there. For instance, so if I had the equation of a plane, and so this might be the equation of a particular plane. Oh, let's see. 1, 1, 1, 1, 8. There you go. Okay. So the point 1, 1, 1 would be in this plane. How do I know? Because 1, 1, 1 makes that a true statement. 0, 4, 0 also makes that a true statement. So that's also a point that is in that plane. 5, 5, 5 is not in this plane. Not going to happen because it doesn't make it equal to 8. Okay. Now, that's kind of a big deal. Okay. And so just going to keep that in mind. Just exactly like back in, I don't know, 3rd grade or whenever some of you smart people learn this. Is the point 1, 8 on the line? Yes. Check. Is the point 2, 19 on the line? No, it's not. Why? Because that's 11. It's not 19. Okay? And so we'll be talking about that. Now, Is it possible to have a line in 3 dimensions? Well, it absolutely is. It absolutely is. Okay? So what I want you to, people sometimes often think, no, Jay, in 3 dimensions is always a plane. That's not true. Okay? When you get on the freeway and you drive down to Wilsonville every of an evening, or whenever you come down, you are driving in 3-dimensional space and you're driving in a straight line. You are not on just a flat tabletop going ever which way. You're just going in a straight line down I-5 or whatever. Okay. Now, in the case of what we're going to be talking about, okay, when we start thinking about this way, we're going to kind of write it a funny different way. In Calc 4, we get into this a lot deeper, okay, than we're going to talk about in this particular case here. But for instance, I could write this out, okay? 3 plus 2t and y equals 1 minus t and z equals 4 minus t. That is, each one of them is dependent on t. We call this, you might recall, a parametric equation. That is, the parameter is time. Okay? Time's obviously very important. I've driven across the railroad tracks many times. I've yet to be hit by a train because the train and I, although we were at the same XYZ location in multiple times, we have not been there at the exact same time. That's the only time it becomes a problem for us. Okay? So when I look at this thing here, okay, first thing I see is I see actually 3 vectors. Let's see if you see them. Here's one vector. Here's another vector. And then here's another vector. Times, and then t, if you will, almost becomes our scalar. That makes sense? And so what we're saying here is this. We are saying that you pick a t value. All right, I pick t equals 2. Sweet. For t equals 2, then my x, y, z becomes 7. My y would be -1, and my z would be 2. Right? Piece of cake. And of course, you can put 3, 4, 5 in. The idea here is that each one of these, every time I do this right here, this whole vector right here, this vector right here becomes my slopes, yes? Okay? This is the slope. It's the change in y, or the change in x rather, with respect to t. And this is the change in y with respect to t. And this is the change in z with respect to t. So kind of keep those in mind as we go along, okay? The parametric equations for the equation of a line is kind of a big deal. Okay? Now, if I had told you this in 2 dimensions, you're like, oh, okay, cool. Turns out. So suppose you said x equals, I don't know, 2 plus 5t, and y equals 3 minus t, or whatever, okay? What you'll notice here is that t is equal to what? Well, it looks like to me t is equal to x minus 2 over 5, yes? And t is also equal to 3 minus y, looks like. Well, if that's what t's are equal to, then guess what? This guy here is equal to this guy here. And if you do a little substitution or distributing, well, you could solve this equation if you want to. I mean, you could do something like this. You could x plus 5y equals 17. That's cute. Or you could rewrite it like this, 17 minus x over 5. And there it is in y equals mx plus b format if you like that better. And what have you done? Well, you've eliminated the parameter. Okay, in this case here, you've rewritten it so that x is not a function of t and y is not a function of t. In this case, we've written it as y is a function of x, yes? You tell me an x, I'll give you a y. This, in this case, is cool because if you tell me where you are on the x-axis, I can tell you where you are on the y-axis. What sucks about not having a parameter is I don't know when this happens, okay? Now then the question, of course, is, well, could you do this in 3 dimensions? Kind of. kind of. Here's the problem with 3 dimensions. If you did this in 3 dimensions, you'd have something like, I don't know, t equals 2 plus z. So you could set them all equal to one another. What does that even say? I don't even know what that says. Sure, whatever. That's nice, but you can never combine the z's with the y's and the x's all at the same time. Does that make sense? So you can't get rid of it. There's too many, you know what I'm saying? You cannot get rid of completely the entire parameter setup, okay? So just be aware of that scenario there, okay? I mean, you kind of, it's tricky, but you can't really do it, okay? So I could rewrite this. Obviously, I could look at these 2 guys here, and I could write y as a function of z, for instance. I could take these 2 guys here, and I could rewrite it as what? Y is a function of x. I could take the outer 2, and I can write z as a function of x. But what I cannot really do is I cannot really get it down to where they're all 3 in the same equation, do it that way. So in this regard, we're typically just going to leave it into the parametrics if we're in 3 dimensions, okay? But again, that's if it's a actual equation of a line. Now, what if we were talking about it in terms of a plane? Okay. Now, a couple things I'd like to talk about here. There's a couple ways I like to do this. Okay. So in 2 dimensions, you may remember this. At some point, you've seen this. Obviously, y minus y1 over x minus x1. That is literally the definition of slope. It's also, if you will, what's referred to sometimes as the point slope form. This piece right here is referred to as point slope equation of a line. Okay. So this is something that, we used to really teach the heck out of this when I was a kid. When I was a young person, we taught this until we were blue in the face. We made a big deal about this. Okay. I'd like to show a couple things here. First of all, this is still a line, no matter how you slice it. This is a line. This is a line. Everything we're doing is a line. These are all algebraically equivalent. So I could also do this. That's also algebraically equivalent, right? I treat this as a unit, and I move it to the other side. Okay? Those are all out. These are still a line. Okay? So we're still in 2 dimensions. Everyone pretty cool with that? Now, what I'd like to look at is this. When I start looking at these things here and I start kind of digesting what's happening here, there's a couple things that come to mind. Okay? First of all, I could rewrite this thing like this. Allow me to make a plus and then a minus right there, for reasons that maybe are not obvious right now. Okay? So what I'm going to get is this. I'm going to get m negative 1 dot, dot x minus x1, y minus y1. Okay? What are you saying, Jay? I'm saying if you take this vector and you dot product with this vector, you get m times this plus this times this. Nice. Okay? And of course, if you want to write it as, if you'd rather write it as row vectors, knock yourself out. It doesn't make any difference. Don't care how you dot it. Most books typically write it as a column vector, but you do you if that makes you happier. Right? Now, what I'm going to do is I'm going to break this second one into 2 pieces, because to me, this looks like parentheses x, y minus x1, y1, like so. Does that make sense? Okay. Now you're like, what are you saying? What are you saying? Okay, this is what I'm saying. What I'm saying is when I look at this, I have, this is obviously a vector x, y minus a vector x1, y1. When we subtract vectors, again, we did this last time we were in class, 2, 1, minus, I don't know, 1, 6. Okay, well, that's just going to be 2 minus 1 is 1, and 1 minus 6 is negative 5. And of course, I wrote those as a row vector, but I could just as easily have written it this way. One negative 5. Okay, that's all we're doing. So I just broke it out this way. And you're like, oh, well, that's kind of cool, I guess. Now, wait a minute. This looks an awful lot like something like this. What if I had A dot B minus C? This looks like the distributive property. I feel like I could distribute it. You can. And this is how you do that. You would get M1 like so, dot xy minus M negative 1 dot x1 y1 like so. Okay, and then this is what we add this amount to the other side. So what you end up with is this guy right here equals this guy right here. And you're like, what? Stick with me. I got you. You're going to see what I'm talking about in just a minute. Okay? Now remember, these are dot products. Don't screw that up. I almost, in my mind, screwed that up. So I want to make sure we're clear on that. Okay? Now, as we're doing this today, I want you to feel comfortable, and you will get comfortable on this. Okay? But these different vectors that I just wrote down have some names. So let me introduce you to their names. Okay? Because once you see them, you can't unsee them. Okay, this guy here, this first guy, where do I want to write it? I think I'm going to write it right here. I'm going to change colors. This first vector here, go away, you hippie. Oh, shoot, rats. This guy right here is vector n dot. And this is I'm using the ones that your book's using so that you're comfortable with it. X minus P. So when you get down here, what you will find is you get NP, N dot P rather, is equal to N dot, N dot X. Sorry. And they're the same, but let me just write the way the book writes it. There you go. Okay. Now, what is this? This is the equation of a line in vector form. Now you're like, why? Why can't I just stick in y equals m or y equals mx plus b form? Newsflash, you just did. Let me show it to you in a minute, okay? Number one. Number two, we are preparing for multiple dimensions because guess what? In the next section, or in the next thing we're going to do is we're going to jump into, hey, let's do it in 3D, okay? But when we're talking about quote unquote a line in 2 dimensions, when we do what we just did and we take it to 3 dimensions, that becomes a plane, okay? And I want to make sure we're clear on that, so I'm going to harp on this. I'm going to give you several other examples of it. Just apologies, my poor throat's killing me today. My voice is gone, I should say. Okay, so let's say we had this equation here. Let's start off with one. Let's say that we have a situation where we have been where's my freaking pen? There it is. Okay, so let's say we have this equation here. You have the equation of a line. Is that what I want? No. Let's start off with we have a slope. Let's say we have a slope given to us. The slope is equal to, our slope is, what is our slope? Our slope is -5. Sure, why not? And we're going to go through the point 2, -3. Okay? So if you recall back in the day, you would go, all right, y equals mx plus b. And you can go y equals -5 5x plus b. Then you plug your points in. And you get something like that. That's how you do it. Well, what we're going to do is slightly different than that. We're going to jump in because, again, we're practicing for where we're going. So we're going to put in our n. So our n matrix, or vector rather, is always the slope and then always a -1. Always. This vector is always x, y, and this vector is your initial point. Wait, that's it? That's it, baby. Let's take the dot product. Boom. -5x minus y, sweet, is equal to, if you distribute that, you get -10 plus 3. And so you get -5x minus y is equal to -7. And I feel like if you were to solve this, you'd get y equals -5x plus 7. It's a different way of doing it. You with me? It's nothing but a different way of doing it. Now, a couple things. We're getting ready for 3 dimensions because in 3 dimensions, it is a bear sometimes to come up with this. Number 1. And then number 2, excuse me. Number 2, when we start looking at these things, we're going to start talking about, okay, well, there's going to be a couple of cool things. Like this vector n is kind of funky, and we're going to look at it in a minute. We're going to see, hey, what's up with that? Because it's kind of strange, okay? And it's always going to be true, and you're going to notice that coming up. There's a reason it's called n, by the way. We're going to learn about that in a few minutes, okay? Also, in 3 dimensions, this just becomes way, way, way easier to do it this way. So you just get in the habit to do it this way, and you're like, oh, oof, piece of cake, okay? So pretty easy to do, okay? Let's take a look at this one here for a minute. So y equals -5x. So y equals -5x plus 7. 1, 2, 3, 4, 5, 6, 7, right? Down 5 over 1. There's our equation, right? Piece of cake. But here's my question. What is -5, -1? What does that vector look like? Okay. Well, let's start just for grins right here, shall we? So if I do this, I'd come down 1, 2, 3, 4, 5. Oops. I'm sorry. Let me back the train up here. Yeah, anyway, so let's go back to that vector. What did I write? Here it goes, -5, -1. Now, what does that mean? Okay, it means we're going to go to the left 5 units, and we're going to go down 1 unit. From where, Jay? Well, from anywhere, to be honest with you. But let's say I go from right here. 1, 2, 3, 4, 5. I go back 5, down 1, and I draw that line. What does that look like? Holy crap, it looks like it's what? It looks like it's orthogonal, and in fact, it is. There's another name for that. When we say a vector crosses a plane or line perpendicularly, we say that's a normal vector. And you're like, the normal vector? That's right, the normal vector. Because it doesn't matter if I went this from here to here, if I went from here to here, if I went from here to here, it's all the same vector. Do you understand? Because they're all the same, because they're parallel. The only difference, of course, is where I started from. Okay, there's only one normal vector, that is a vector that's orthogonal to that guy. You're like, well, wait a minute. Are you saying that this guy right here, -5, -1, which is what I have right there, okay? You're saying that it is orthogonal. Wait a minute. I feel like we studied this back in the day at some point. I feel like it seems to me like, gosh, how do I want to say that? It seems to me back in not grade school. Come on, use your, come on, Jay, you got this. The slope of this guy, the slope is negative 5 over 1, right? That's the slope is negative 5 over 1. But what would that be in a vector? Well, it would be going over 1, right? It would be going over 1 and down 5. So what does that tell you right here? This tells you this guy right here is also a vector, yes? What if I took that vector, which is the slope, and what if I dot producted it with this guy? What would I get? Well, you get 5 times that is negative 5 plus 5 is equal to 0. What does that say? It says they are orthogonal or they're normal. Okay? That's a big deal. Now, in multi-dimensional, in 3 dimensions and so on, it really becomes a bigger deal. Okay? Like it's harder to do. Okay? You may recall back in the day that back in like Algebra 1, the teachers would always do things like find the equation of the line that is perpendicular to your line. Well, if my line has a slope of negative 5 over 1, what's the slope of the other line? Well, the slope of the other line is 1/5, right? Because it's the negative reciprocal of that. And we know that when we multiply their slopes, we got negative 1. Remember that? Maybe it's been a while. If you've forgotten, it's no big deal. That's kind of just like bringing up something from the past and talking about it for a minute. Okay? Now, you're like, Jay, that's great. That's great, Jay. Let's chat about this for a little bit more here. Let's take this to another level. So recall that I have mx minus 1, or x minus x1 is y minus y1, like that. What's another name for slope? Another name for slope is dy dx. Right? Now I mentioned that because then the next thing that we did was he said 0 equals dy dx, x minus x1 minus 1 y minus y1, right? And we said that that normal vector would always be of the form dy dx, or if you prefer, m, comma negative 1. Always. Okay? That's a big deal because in 3 dimensions, instead of y, up here, y is a function of x. In 3 dimensions, it's going to be z is a function of x and y. You tell me x and y, I'll tell you what z is. Okay? So we're going to be looking at something along the lines of ax plus by plus cz plus d equals 0. Right? So in other words, instead of ax plus by equals c, or maybe plus c equals 0, whatever you want to call it, we add that z component in there. Okay? So when I do this, let's think about this for a minute. When I write this later on, what I'm going to end up seeing is instead of this thing right here, I'm going to end up with 0 equals dz dx, x minus x1, plus dz dy, y minus y1. That is, how is y changing with respect to z, minus 1, z minus z1. Okay? Now, your normal vector just becomes this. Now, in this class, we're not doing partial derivatives, so you don't have to worry about it, but this is what it always becomes. It is just a mirror image of what we're seeing in 2 dimensions, taken up to 3 dimensions. That's it. Now, it doesn't really matter what these values are. They could just as easily have been actual numbers, a, b, c. I'm sorry, a, b, negative 1, let's say. Okay? Whatever they are. Of course, I could multiply through by constants, right? So I could take and then multiply this through by some value, 5, let's say. Well, guess what? This is no longer negative 1 down here. Are you with me? So I might have some 5a plus 5b negative 5. In other words, those are just the same. They're the same function. They're the same vector. I've just changed their lengths, if you will, right? So when we do this, what we're going to see is we're going to have some normal vector, and the way your book introduces it, because again, we are not doing derivatives, but I want you to see that that's all that was a slope. It was a change. It's the rate of change of y with respect to x. In 3 dimensions, it's a change in z with respect to x. It's a change in z with respect to y. And then, of course, you got that -1 component there. Okay? The way the book writes it, they just do ABC. Okay? In other words, again, we could have multiplied through by any number. It doesn't have to always be that -1 at the bottom. Okay? And then, of course, what are you going to have? Well, you're going to have times. Okay, what's going to? So that's my. I'm sorry, that's my n. Okay, and then you're going to have your x vector. All right, cool. So x, y, z. And then you're going to have your p vector, which is going to be some x naught, y naught, z naught. That is some initial value. So if I say to you, I want the plane passing through, I don't know, 2, 1, 5. Sweet. And with a normal vector equal 2, 1, 4, then you're literally going to write 2, 1, 4 dot x, y, z equals 2, 1, 4 dot 2, 1, 5. Okay? If you dot this out, you're going to get 2x plus y plus 4z is equal to 4 plus 1 plus 20. So 2x plus y plus 4z is equal to 25. Or if you're weird, subtract 25 over here, set it equal to 0. Or if you're weird, z equals 25 minus 2x minus y divided by 4. Right? So you could rewrite that. They're all algebraically equivalent. So not to panic. What would happen? What would happen if I took the point? I want to put this back to 25, I think. What would happen if I asked you, hey, listen, is the point 1, 2, 5, is it on this plane? I don't know. 2 times 1 is 2, plus 2 is 4, plus 20, that's 24. That's not 25. So, no, it's not on the plane. Okay? And any point that would make that a true statement will be on that plane. Make sense? Now, what does that normal vector look like on a plane? Well, if I had a plane doing its thing here like this, the vector would be sticking out of it normally right here. Okay? So it'd be like standing in front of the chalkboard and all of a sudden some 2x4 jumps out of the chalkboard and smacks you right in the head. That would be a vector. Okay? It'd be sticking out parallel to the perpendicular to the board, just pop right out, and there it is. Okay? Yeah, it's pretty easy to do. Let's say you're sitting in the back of the classroom, you shoot a spit wad, good for you. It lands on the chalkboard. The path, let's say that it took straight into the board because you shot it perpendicular to the board, good for you. That'd be your normal vector. That vector could come out of the board, it could go into the board, either way, right? Because really potato, vodka, right? In fact, if you came up here, what if I changed these and made them negative? Is it going to change anything? I think it's pretty clear that all I did was throw negatives in there, and it's all going to come out in the wash. Oh, look, they're all negative. OMG, gosh, negative, negative, negative. Oh, look, oh my gosh, they're all negative. But they're the same, okay? So it wouldn't matter if we had the going into the chalkboard or coming out of the chalkboard. A normal vector is a normal vector. It's not going to be hurt by anything, okay? Now, let me do a couple problems that are very similar to book problems so that you feel comfortable with them, hopefully. And then there's one or two other forms that I want to just show you because sometimes people get a little confused. Well, not really confused. They get a little sometimes weirded out by it. Here we go. This one. Sure, I like that. Sweet. That's hot. So it goes through the point. And so they say P equals this guy, -3, 1, 2, and has a normal vector of 1, 0, 5. Beautiful. So I'm literally going to go boom, 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 1, 0, 5 dot x, y, z equals 1, 0, 5 dot -3, 1, 2. Okay. If you do that, if you distribute these out, you're going to get x, there's no y, plus 5z is equal to negative 3 plus 10. So x plus 5z is equal to 7. It's pretty much that easy. Okay, I wish I could make it harder. I just can't do it. I'm sorry. It's pretty straightforward there. Okay. Now, this next one's a little trickier. So I'll see if I can help you out on this one here. It's a little weird. A little weird. It's not terrible. It's a little weird. Okay. Oh, excuse me. I'm gonna die. It's terrible. Okay, now, as I mentioned previously, if I gave you 3 points, you could find at least 2 vectors. And so later on, we're going to find out how to find the normal vector right away. Okay? That's not taught at this juncture, and I don't want to confuse things. We'll come back and hit it again. There is another way. Suppose I just told you, hey, there's 3 points. Oh, okay, what are they, Jay? 2, 1, 4. 3, 2, 8. Negative 1, negative 2, 7. Hot diggity. Is there a way to find the equation of this plane, okay? Is there a way to find it just using this information? And the answer is yes. Yes, there is, okay? And so it's a vector format, and I'll show you how it works in a second here as we get going. It's a little tricky. It's a harder way of going about it, but at this juncture, that's all you have to deal with, okay? If I could find quickly, obviously I can find these vectors. That's easy to do. If I could find a quick way to find the normal vector, we're home free. That makes sense? Finding that vector is kind of a bear sometimes. And so let me show you the other way to go about it, okay? Okay. So when we do problems like this, okay, we know that these lie in a plane somewhere. Okay, what we're going to end up doing, we're going to end up writing a function that looks a little different than what we think about, okay? So what we know is we need to go from some random starting point. We need to go out this direction, be able to go out this direction in some fashion, and out this direction is some other direction in some fashion, okay? Some other vector. If I go out here just a little bit and I go up here a little further, I'm going to get this point here. And I go over here a little bit more, I get another point. And over here, not up as far, I'm going to get points. Basically, I'm going to fill in points all over this plane, yes? So, for instance, I could make this vector, this direction, I could make it shorter by multiplying it by a scalar. Maybe I only come in this far. And maybe I make this guy not go up at all, and I get that point right there. And maybe I want some points over here, so I go on this one in a negative direction. Okay, maybe I go on this one in a negative direction. It puts me down in here somewhere. The idea is that you're going to pick a couple of vectors, say this vector and this vector here, and you're going to be able to extend them out as far as you want, or maybe negative as far as you want. And you're going to go, okay, well, first I'm going to go out here some distance, boom, and I'm going to come up here some distance, boom, and that's going to be a point that I'm going to graph. And when I fill in all of these points, the collection of all these points that I'm going to make by doing this is going to be a what? Well, it's going to be the plane. Okay? And so when you think about this, that's always going to be true. So for instance, in our everyday world, you could think of this 1, 0 vector, this guy right here, and you could think of this vector right here, 0, 1. I could think of them as being able to produce the entire x, y plane, the entire plane. How would I do that? Well, for instance, let's suppose I want to get the point 4, 4. All right, cool. I would take 4 times this fella, 4 times this fella, and that's where I would land. What if I wanted to get the point -2, 8? Well, I would take -2 times this one, and then I go up 8 that one, and I would get that point right there. And if I did it an infinite number of times and places, I would end up creating the entire XY plane. That's a big deal, that bit right there. That thing right there is huge. And in fact, that is something that we call we could say this. We could say that in this case, we could say that X and Y is equal to A times 1, 0 plus b times 0, 1. That creates the entire xy plane. What we're saying here, this right here is what's called a linear combination. That is, I take a number, 2, 3, 5, whatever I want, 0.7, whatever, 0 if you like, pi if you want to, a constant, a scalar, if you will, a, times 1, 0, plus a different scalar times 0, 1, and I add them together. And when I do that an infinite number of times, what I will reproduce is the entire xy plane. That's a big deal. Okay? That's not true for every set of vectors. For instance, suppose you had the vector 1, 1 and the vector 2, 2. Well, Jay, those vectors go the same direction. They sure do. So if you were to add and subtract these vectors together, all you would ever get is points where? On this line. Would that produce the entire xy plane? It wouldn't produce the xy plane. That's a big deal. Okay? And so what we're going to look at here is the foundation for what we're going to see in the next 3 or 4 chapters. Okay? So the first time I ever taught this class, this second way of teaching planes, it kind of pissed me off because I'm like, there's a better way to do this. Why are you doing it? Okay? But then I realized after the first time I taught it, I'm like, oh, geez. What it's actually doing is it's showing you that there are certain vectors that I can use and add them together, multiples of them, and create the entire xy plane. And now you're like, wait, like, give me another one. Okay, well, 1, 1, for instance. Any vector that is not parallel to 1, 1 will produce a linear combination with that guy, will produce the entire xy plane. 1, 0, for instance. Okay. Now, we'll get into prove why this works later on, but it's pretty clear that I can go out at an angle anywhere along this 45 degree, like so. Okay. And any multiple thereof, you with me? Any multiple thereof. And what I can end up doing is then go over, back, and I can find any point on the plane that I want to end up at. Okay, I think I can produce any single one of them. Okay, so you're like, well, what about 0, 10? Can you produce that, Jay? I think so. I believe I can. 0, 10. I think so. Let's see what I'd have to do. Well, I would need to get a 0 on the first term, and I need to get a 10 on the y. Well, I feel like if I did 10 plus 0, not plus 10, plus, you dumbass, plus negative 10, eh? That would give me 10 minus 10 is 0 on top, and it would give me 10 plus 0 is 10 on the bottom, 0, 10. Yay! And what does that mean to me? Well, it means that all I have to do is take this vector here, and I go negative 10 this direction, and then I would go, if I multiply this by 10, I would go back 10, 10, and guess where I'd end up? Boom, 0, 10. Boom, that's where I'd end up. That vector right there, that's the point. And I could produce any point on this entire xy plane. The only ones it wouldn't be true for is if they were parallel to one another. Does that make sense? If you had two vectors that were parallel, you could never reproduce anything that's off that line. But if they are non-parallel, whatever, I can produce any point on this entire graph. That is a big deal. That is fundamental. Okay, I'm going to go ahead and tell you the name of this. That means they form a basis. Okay, and later on you'll be like, oh, I got this, because it's the easiest thing on the planet. Okay, but again, when I first taught this class and I saw this method of teaching how to write a plane, I was so pissed off. I was like, why would you do it this way? And it wasn't until much later that I'm like, oh, I see, said the blind man. I like it. I like it a lot. Okay, now, just as an aside, could you have three-dimensional vectors that create all of 3D space? And the answer, of course, is obviously yes. Yes, you could. I think it's pretty obvious that if you had 1, 0, 0, 0, 1, 0, 0, 0, 1, for instance, it's very obvious that those three guys right there would create all of x, y, and z space. If you multiply this one by 10, this one by 5, and this one by 2, you'll end up with the point 10, 5, 2, obviously. And you can do the same thing for any other one of them, okay? And so later on, we'll get into, hey, do these vectors form a basis? In other words, can you create all of 2D space? Can you create all of 3D space? Can you create all of 4D space from the vectors that you've been given? Okay, that's a big deal. Now, what we're going to be looking at today, though, is slightly, I mean, it's the same thing, but it's kind of, again, we're doing the equation of a plane. We're doing it starting from a couple of points, or 3 points rather, and then we're going to be working our way out. Okay, so it's going to be kind of cool, and you'll see what I mean as I get into this. So the equation I'm going to write down is this guy here. X is equal to P plus S. You're like, what the heck is S? Just, I got you. Just calm down. I got you. Plus T V. Okay? Now, what do I mean by that? Well, what I mean by that is this. We have over here, I'm going to put down some points again. I don't know if I remember if I start with points or not, but I'm going to grab some points. So let's say I had the points 1, 1, 1, 2, 4, 9, 6, 7, 3. Okay? Can you find two vectors? Yes. Let's call these A, B, and C. Let's find vector AB. So from A to B, I'm going to go over 1, I'm going to go up 3, and I'm going to go up 8. Does that make sense? And I'm going to call this vector U. I'm just going to define it to be vector U. And then I'm going to pick, I'm going to go BC, and BC is going to go over 4, 3, negative 6. And I'm going to define this to be vector V. Okay? And you're like, what? The Sam Hill's going on, Jay? Well, here, I'll tell you right now. Here's what's happening. We're going to start at point P. Okay, well, what is point P? Well, point P was a point. Okay, well, what point do I want to use? I don't know. Let's start at 1, 1, 1. Okay. And what do you want to add to that? Well, I'm going to add S, whatever the Fink S is, 1, 3, and 8, plus T, and then my V vector is 4, 3, negative 6. Okay, this is the equation of a plane. Okay, how do I know that? I'm starting at any location. That's my P location. Okay, and I'm starting there, and I'm going to go out in the direction of 1, 3, 8, and I'm going to go out how far? Exactly as far as I want to go out. Okay, maybe I want to go twice as long, maybe 3 times as long, whatever. And I want to go out this direction. Let's just say T. This is T. And I'm going to go out 1, 2, 3 T, whatever it is. And so if I go out up here and then I go out to here, I end up at that point out there. That is a point that is on the plane. Okay? So when I look at this, again, T and S can be any scalar amounts. So for instance, let's find where we are. Where are we? X, Y, Z, that is. Where are we when S equals 2 and T equals 4? I don't know. Let's find out. So it's going to be 1 plus 2 plus 16 is 19 in the X direction. In the Y direction, it's going to be 6. And 12 is 18 plus 1 is 19. Hey, that's pretty cool. Didn't mean to do that. And then it's going to be 16 minus 24 is negative 8 plus 1 is negative 7. That's where we would be. You're like, but what if S is 0? I don't know. What if S is 0? And what if Y is, T rather, what if T is equal to 1? I don't know. Then I guess I'm going to get an X, Y, Z place of 5. So 1 plus 4 is 5. 1 plus 3 is 4. 1 minus 6 is negative 5. And that's where I would be. And I could then create this entire plane from this setup. This is the equation of that plane. It's called a parametric equation. My parameters this time are S and T. Okay, my parameters are s and t. It is no different than on this previous page when we were putting on over here the a and b. There's no difference. There's zero difference. Now, Jay, how do I know that these vectors aren't perpendicular or aren't parallel? Well, the only way they could possibly be parallel is if these 3 points were what we call collinear. They're on a line. Okay? As long as they're not on a line, we're gooch. Okay? We are Gucci there. Okay? Let's try another one. Let's say you had these points 2, 1, 7, 3, 6, -1, 2, 2, 2, whatever. Don't care. Doesn't matter. Okay? Then x, again, that's a vector, which really just means x, y, z, if you will. That's what it really means. X is equal to, I need a starting location, so pick one. Doesn't make any difference to me which one you pick. And then we're going to say u, we're going to say s, rather, times our u vector. And so what is our u vector? Let's say our u vector is going from here to there. So from 2 to 3 is 1. From 1 to 6 is 5. From 7 to -1 is -8. That's an S, by the way. I find it annoying when they use S's because I cannot write an S to save my life. And for hypothetical purposes, let's say that my V vector is from there to there. Okay, I went 2 to 2 is 0. 1 to 2 is 1. 7 to 2 is -5. This is right here. That is my parameterized equation. Okay. For the plane. And if I said, well, let's let s equal 1 and let's let t equal -1. Okay, then where would I end up? Well, I would end up at 3. And if s was 1, I'd get a 5. -1, that'd be 4. Plus 1 is 5. And then s is 1, so that'd be -8. Plus 5 is -3. Plus 7 is +4, I guess. That's where I would end up in that case. Okay? Again, this idea of a linear combination is a big deal. That is, a linear combination means you take a scalar times a vector plus a scalar times a vector plus dot as many times as you want to. As many times as you want to. You could do 3 of them. Bitchin'. Nice. These could be 2-dimensional vectors. They could be 3-dimensional vectors. They could be 4-dimensional vectors. Doesn't matter. What we'll find in this text is that frequently, if we're going to do a linear combination of 2 vectors, they're 2-dimensional vectors. Okay, it's 1, 2. If we're doing 3 vectors, we're typically going to be doing 3-dimensional vectors. 4-dimensional, etc. But it doesn't really change how we go about doing it. Okay, so that's section 1.3. Okay, and again, I cannot stress this enough that now that I've taught this class, 7 times or whatever it is, this makes a lot more sense to me in terms of why we do it this way. Because literally, the rest of the text, we're going to spend oodles and oodles and oodles of time talking about, do these vectors form a basis for all of 2D space or for whatever it is we're doing. And we'll be talking about that a ton going forward. Okay, a ton going forward. And so that's kind of a big deal. Okay, kind of a big deal. It's very similar. You're like, Jay, but when you wrote that out before, you didn't include this guy. Oh, you're absolutely right. This guy here is what keeps it pinned down in a plane, and it's not all of 2D space. Wait, how do you know that? I know that because we started at a point. Okay, we started at a specific point, and therefore we can only construct a 2-dimensional flat plane across the board, whatever it is, happens to be. Okay, so it's a little bit, it looks a little different than what we're talking about on the previous page, but it's the same basic principle. Okay, now the last thing I wanted to talk about was in 2.1 yesterday when we were in class. We did a couple of these guys. So we had 2x plus y equals 9, 3x minus 7y equals 16, or whatever it was. And so we created an augmented matrix. And I want to show you, just for fun, again, just a quick reminder of how it went down. Okay. Now, me personally, this is how I like to do it. I need to get a 0 here. Okay, so for me, I'm going to take 3R1 minus 2R2. And I write that there, and I write my answer down here. Again, I don't touch the top row. And then I'm going to take, it's going to be 6 minus 6 is 0. And then 3 times 1 is 3 minus a minus 14, so plus 17. And then I'm going to get 3 times 9 is 27. Minus 32 is negative 5. That's how I like to do it. You'll find that a lot of books will do the same thing, but they'll write it here. That confuses me, but you're welcome to do it any way you want to. This is for your benefit, not mine. So I like to write up here what I'm doing, and then my answer is down here. Okay, but you do you. I don't care. I will figure it out. If you need my help, I got you. Okay. Now, at this juncture, I really would like to have a 1 there. So you're like, well, divide by 17. You are more than welcome to do that. The problem that you're going to run into is that when you do that, you're going to end up with a fraction here, which is disgusting. Then when you go to eliminate here, you're going to have another fraction. Gross. So fight the desire to do that. Unless this was 17. If this was 17, hey, you're gooch. It's 1. That's nice. But it's not. It's negative 5. Okay, so what I'm going to do now, I'm going to get me a 0 right there. So what I'm going to do is I'm going to do 17R1 minus R2. That's what I'm going to do. So when I do that, I'm going to get 17 times 2 is 34. Minus 0 is obviously 34. Bottom row not changing this time. 17 minus 17 is 0. 17 times 9. Holy crap. Who came up with that stupid problem? 63, 153. 153 minus a minus 5 is 158. What a stupid problem. So clearly divide by 34, divide by 17. Hey, you're home free, baby. So you get this 0, 1, negative 5 17ths. That's my y, obviously. 1, 0, 158 34ths, whatever the think that is. Okay, and there's your 2 answers. Again, I don't care how you do it, but for me, this is what I'm doing to get from here to here. Again, a lot of the textbooks, including yours, will write this down here where the answer was, and that confuses the bejesus out of me. Okay, I don't like that. But again, you do you. Okay, it's a very much it's how you do it. It's you're doing the same thing. It's how are you communicating it, and specifically, you're communicating it to yourself, not to me. I couldn't care less. I couldn't care less. Okay, I'm just gonna play along, have some fun with it. Okay, so again, up to you. I had a guy last year got all mad about that, and I'm like, dude, it's just notation of where you're just keeping track of what you did. Okay? Because here's what's going to happen. You're going to make a boo-boo somewhere. You're not going to subtract correctly. Ah, crap. And then now you're screwed. You're like, you go back. Oh, yeah, what did I do? Oh, I did 2R1. Oh, sure. And it's just a way of going back and checking yourself. Okay? So it's neither for me nor the book. No one's going to grade you down on that. Boom, done. All right? Yay, that's what I'm all about. If I get down here and I see that and I go up here and I go, yeah, it looks like this is the correct amount of work on the test, nice. If I see some random BS through here and then all of a sudden the right answer pops out, nah, not going to happen. Okay. But if I see you're doing the right thing, maybe you went a little different than me. Maybe you're a weirdo. I'm not judging. I'm just saying. Maybe you did 2/3 R1 minus R2. Oops. Ass backwards. 3/2 R1. Will that work? Sure will. Do I want to see it that way? Boy, I wouldn't do it that way, but knock yourself out. If you did it that way and you don't screw it up, you will get the right answer. Okay? But me personally, I would have just done 3R1 minus 2R2. But again, you do you. Okay? All right. I think that'll take care of us for tonight. Look at that. Right under an hour. Dude, you're an animal. Let's see if you can kill 15 more seconds. I'm not going to do that.